Hello everybody, this is Professor Iris Miano giving you your Geometry Math 32 at SMC. I believe we are week 11, day 20 lecture video on sections 7.4 and 7.5, and this will conclude chapter 7 material, which will be the entirety of exam 4's content. So just to be clear, exam 4 will only be covering, technically, sections 7.2 through 7.5. All right, so here's the wrap up on that material. And we're going to have an entire section, as you can see in 7.4, dedicated to the Pythagorean theorem. And then the last section in chapter 7 will be dedicated to special right triangles. So those are your 45-45 90s and 30-60 90s. So if you already have a little bit of a background in special right triangles, then this will be good review for you. And if you don't worry, I'm here to teach you all about it. And then so let's go ahead and dive into the Pythagorean theorem, but let's get a little bit deeper than simply the baseline information of a squared plus b squared equals c squared. What else can we be doing with the Pythagorean theorem? Well, it just so happens that if you take a right triangle and you draw an altitude to the hypotenuse from the right angle, you get two other right triangles inside of it that are similar to each other and to the original right triangle. And that's exactly what this first theorem in section 7.4 outlines. So I have a visual that I want to present to you that illustrates what's being said in this theorem. So take yourself, give yourself a generic right triangle, okay? I believe you have the same one in your lecture notes here. And then we'll want to add an altitude from, so it needs to start from, where's my cursor? There it is. It needs to start from the right angle, right here, this vertex where the right angle is, and it needs to hit the hypotenuse, which is this longest side here, in such a way that it forms a right angle. It needs to be perpendicular, like so. Okay, so here is the altitude, this extra line that just got incorporated. Okay, and we know it's an altitude because it hits the hypotenuse perpendicularly, and therefore right angles are formed. So here are all the possible right angles that are happening here. Okay, so you may notice that there's two new triangles inside of what we would call the main triangle. In fact, since there's three triangles altogether and they have relative sizes to one another, I call them the mommy right triangle, like the middle-sized one among the three. Here's the baby right triangle in orange. So mommy is blue, baby is orange, and then the daddy right triangle was the original right triangle in the first place. So sometimes I'll refer to them this way just for ease of description. Also, if you know the idea of this, conventional nuclear family is not appropriate or feels funny to you, by all means call it the large, the medium, small right triangle. I don't know why, it just fits well from my perspective to call them the mommy, the baby, and the daddy. But large, medium, and small also do fine to describe the three triangles in play, with the incorporation of the altitude draw from the right angle to the hypotenuse. Okay, so what can you do with this? Well, all three triangles in play are similar to each other, so that opens up a wide array of different conclusions that you can draw, and here are some of the specific ones in the form of other theorems. So here's the second theorem in this section, in which we outline how if you take a right triangle ABC as seen here, and you draw that same altitude from the hypotenuse, right, to the from the right angle to the hypotenuse, that is, and I'm going to go ahead and have that altitude necessitate adding another point D here, right? So we can effectively name the small and medium right triangles, right, that come into play with the incorporation of this altitude. Then what do we get to say? The altitude of the hypotenuse of the right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Ooh, so this phrasing, geometric mean, is something that has not been introduced just yet. So what does it mean? What is the geometric mean? Well, you may know what the mean is as far as like a collection of values is concerned. Just a regular mean, the arithmetic mean, in fact, is just the sum of all the values in a data set divided by the number of data values that you have. But the geometric mean is a proportion that you set up. And it's, okay, so let me just show you the geometric mean of the lengths of the segments of the hypotenuse. So the segments of the hypotenuse in this configuration here, one segment is AD and the other segment is DB. Collectively, they make up the hypotenuse AB. You guys see that? So when I talk about the segments of the hypotenuse, I'm talking about AD and DB, or BD, depending on how you want to name this. If you want to name the line segments always in, alphabetical order, then the longer segment would be named DB. Or sorry, BD, rather. Okay, BD. So anyway, how do we set up this geometric mean? Like I said, it's a proportion, which is two ratios equal to each other. So the length of the altitude of the hypotenuse, what's the altitude? That's line segment CD, okay? If it is the geometric means of the lengths of the segments of the hypotenuse, then we're going to have certain elements that we need to take into account. So here in red, I've lit up the altitude. Okay, so the altitude is supposed to be the geometric mean of the lengths of the segments of the hypotenuse. So let me light up the segments in green and blue respectively. The shorter segment is AD, lit up in green, and the longer segment is DB, I guess is the way I was thinking about naming it, because I was probably just going in order with the points going from the tippity top to the bottom of the hypotenuse. Okay, so what does this mean? So when you see this phrase geometric mean, it is referring to a proportion, which is what you see here where my cursor is circling. And the thing that is mentioned as the geometric mean, which in this case is the altitude. The altitude is the geometric mean because it's in the mean positions. Yes, so when you have a single proportion, just two, not a string proportion, but two ratios set equal to each other, then the denominator of the left side and the numerator of the right side, those two positions in the two ratios are the means positions, okay? And the extremes positions, this is terminology that is something that I'm hoping that everybody has some familiarity with. And if you're just looking at this and you're like, I've never heard this before in my life, don't worry, that's why I'm here to teach you this. So AD and DB, the two segments of the hypotenuse, those values are in what we call the extremes positions, which is the numerator of the left side, denominator of the right side of the proportion equation, okay? So this is the way that you would set up the proportion based on the description of this theorem. So let me click back actually to everything here just to review everything one more time, because it's a lot. It's a lot. You're being introduced with this phrasing geometric mean, and it is alluding to a very specific configuration of line segments according to some proportion, right? So what is the geometric mean? Again, it is going to be a proportion in which you take, the first thing that's mentioned is the altitude, which I'm going to highlight in red, CD. This CD is the geometric mean of the lengths of the two segments of the hypotenuse. So the shorter segment is AD, the longer segment is DB, lit up in green and blue respectively. So to say that the altitude is the geometric mean, so it gets repeated in the two means positions, which are the bottom position, you could say, or the denominator of the left-hand side of the proportion, and the numerator, or top position, of the right-hand side of the proportion. The geometric mean, CD, which is the altitude, that's going to be the geometric mean of the lengths of the segments of the hypotenuse, which are AD, right here, that's one segment of the hypotenuse, and DB is the other segment of the hypotenuse. So what this theorem is stating is that there's a relationship between the altitude and the segments of the hypotenuse that come about with the incorporation of this altitude, because the altitude has to meet the hypotenuse at some certain point in order for it to be perpendicular to the hypotenuse itself. So the location of D, right, on the line segment AB, the hypotenuse, cuts the hypotenuse into two distinct segments. So that's what the values are that go in the extreme positions of the geometric mean, okay? So what's the purpose of this? Well, you might have some instance in which you are asked to find either the length of the hypotenuse or the segment of one or the other segments of the hypotenuse, and all the other values are known. And so as long as you know this relationship, you could set up this proportion in order to find that unknown value, okay? Great. There's more. Okay, so remember the setup with the geometric mean because it's going to come about in the next theorem as well. Okay, here we go. Actually, it's a lemma, so it's a little bit of a subtheorem. It says the length of each leg of a right triangle. Now remember, right triangles have two legs. Those are just the, not the hypotenuse edges of the right triangle. And there's two of them and they need not be the same length, okay? Each leg of the right triangle is the geometric mean. So again, we're going to set up a proportion and we're going to do it two different ways, okay? Because there's two legs for each right triangle. So that means there's two different geometric mean proportion equations that we can set up. So stay tuned for that. There's a space on your lecture notes to write the two different ways. So each leg of the right triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to that leg. Like what is even being stated here? Don't worry, I have a color-coded demonstration that's going to help you set up the proportions that describe this geometric mean relationship. Okay, so here we go. Here's the first one. So in the first figure that you have in the space underneath this lemma, I want you to follow along with me here. And it's helpful if you have colored pencils or markers at your disposal, but it's not necessary at all. Okay, you will see colors on this lecture video, this PowerPoint, because I think it's helpful in illustrating where all of the pieces go in the proportion that's being described with this geometric mean. So here is the first one. Now let's assume that we're talking about the smaller, okay, hypotenuse segment, which I have lit up in yellow, AD, because we're connected to the shorter leg, okay? So this is the geometric mean proportion setup that's being described here associated with the shorter leg. We're going to do this again for the longer leg in the second figure, okay? So let me read this lemma again. The length of each leg, we're going to focus on the shorter leg right now, of a right triangle is the geometric mean. So notice that the shorter leg AC is in the means positions, right? Again, the means positions in this proportion for the geometric mean relationship is in the denominator of the left-hand side and the numerator of the right-hand side. So that's why we have AC in red representing the shorter leg, which is described as the geometric mean in these particular positions repeated. That goes here and it goes here, okay? It's the geometric mean of what? The next two things that are mentioned go in the extremes positions here. So it's the geometric mean of the length of the hypotenuse. So that's AB, the entire length of the hypotenuse. Notice that I have that lit up in blue here in the figure, and it's in the first extreme position. It doesn't matter if you put AB here or there. It just needs to be in one of the extremes positions. And again, just to be clear, the extremes positions are the numerator of the left-hand side and the denominator of the right-hand side. Okay? And what's the other thing that's mentioned? The length of the segment of the hypotenuse adjacent to that leg. We're talking about AD here. AD is the segment of the hypotenuse adjacent to the leg that we chose in the illustration of this particular lemma. Okay? Cool. Now, I'm going to click forward and show you this particular lemma relationship, but in regard to the longer leg BC. Okay? Here we go. Here is the longer leg BC relationship with this particular lemma, okay? Now, the length of the other leg, the longer one BC of a right triangle is the geometric mean, so that means that it is in the means positions. Notice that it's BC in the means position. And what goes in the extremes positions? The length of the hypotenuse, which is still just AB, right? And the length of the segment of the hypotenuse adjacent to that leg. This time, that's going to be BD, okay, which I have right here in yellow in the other extreme position and lit up in yellow in the figure, okay? So hopefully that makes sense, how these are being set up and how it illustrates what is being described here in regard to this phrasing geometric mean. So when something is the geometric mean of two other things, then the thing that's categorized as the geometric mean goes in the mean positions, repeated. Same value in the denominator of the left-hand side and numerator of the right-hand side, okay? And then the other two things that it's the geometric mean of, right, is going to be in the extremes positions, which in this case is the hypotenuse and the segment of the hypotenuse adjacent to that leg. Cool. We can talk about this in more detail in class if we need to. Just let me know. But that's your first introduction to it. All right. Moving on. Next is going to be our old friend Pythagorean theorem, but it's going to be represented in terms of the line segment names themselves, okay? So here we go. The square of the length of the hypotenuse of a right triangle is equal to the sum of the squares of the lengths of his legs. So here it just is represented with colors, and I'm talking about lengths of line segments by having the line segment names with no hats on, okay? But this is old news. Previously it was presented as lowercase letter representations of the lengths of these edges, where this length right here, this leg would be called lowercase a because it's opposite of vertex capital letter A. And then this length in red would be named lowercase b, right, because it's opposite of the vertex uppercase B. And the hypotenuse length is always categorized as lowercase c because it's always opposite the C vertex, which is, conventionally anyway, associated with the right angle. Okay, cool. So this is just another way of representing the Pythagorean theorem in terms of line segment measure names. All right, and okay, I think we're ready to move on to the next theorem, which is to say that if A, B, and C are the lengths of the three sides of a triangle, with C the length of the longest side, and if c squared equals a squared plus b squared, then the triangle is a right triangle with the right angle opposite the side of length c. Okay, so this is kind of like the converse of the Pythagorean theorem, which is to say that if you are given, for this next example, like what we're going to talk about here, three lengths, and you plug them into the Pythagorean theorem and it works, like it satisfies the Pythagorean theorem, then you can say that these three lengths form a right triangle. And that's exactly what we're going to test here in this example. This example states, could the following lengths form a right triangle? So your shortest length is 9, that's your A. Your medium length is 12, which is B. And your longest length always needs to be in the C position. That's very important here, because if this forms a right triangle, the longest length is always going to be the hypotenuse, so it needs to be set equal to the C value put in the C position in the Pythagorean theorem in order for this test to work, okay? So here I go, taking the Pythagorean theorem, and I'm going to replace these values with these letters with the values that are given to me. And notice that I'm putting a little bit of a question mark over the equal sign because I'm not sure if this is going to all work out. I'm testing to see if it's equal. And if it's equal, and by it, I mean if both sides of this equation are the same value, then I will know that the numbers that I plugged in form the edges of a right triangle. So let's simplify. Simplify. Oh, look at that. Both sides of the equation, once I simplify everything down, end up being 225. So they're equal. Yes, check mark makes it so. And so that means that these lengths could form a right triangle. In fact, they do. I guess I could have a little bit of stronger language here and just say these lengths emphatically do form a right triangle. Okay, but that's how you'll test it, and that's the purpose of this theorem. It's more or less the converse of the Pythagorean theorem. Okay, great. Moving on, let's talk about Pythagorean triples. Now, I have mentioned Pythagorean triples in the past just because I felt like it was relevant earlier in the curriculum. But here's the point in which we're going to formally present what Pythagorean triples are. There are a set of three natural numbers, so, you know, no decimals or fractions or anything, no irrational numbers, right, going on for the values of A, B, and C that satisfy the Pythagorean theorem, okay? And so there's some famous ones that I want you guys to get to know. And the most basic and famous one ever is 345. And isn't that cute? The numbers are consecutive, so it's really easy to remember, hopefully. The next largest Pythagorean triple is a 5, 12, 13. Then there's 7, 24, 25, 8, 15, 17, 9, 40, 41, and literally there are infinitely more Pythagorean triples. People are discovering new Pythagorean triples with obscenely large numbers all the time. And also, any scalar multiple of a Pythagorean triple is also itself a Pythagorean triple. Like, for instance, if you multiplied 3, 4, 5, each of these three numbers by 2, you would get what? 6, 8, 10. And 6, 8, 10 is certainly, a Pythagorean triple because it's a scalar multiple of 2 of the 3, 4, 5 original Pythagorean triples. So that's why I say this at the end, and any scalar multiples of these triples are also themselves more Pythagorean triples, and then there's so many more beyond that as well. Literally, super nerds are coming up with more Pythagorean triples with obscenely large numbers even as we speak. Or as you watch this video. It is happening all the time. Okay, next theorem. What do we got here? Let's consider A, B, and C representing the lengths of three sides of a triangle, with C being the longest side. There are two caveats, or two different parts of this theorem, which give the ability for folks to categorize what kind of a triangle you're dealing with. If it's not equal, then you have two options beyond that. Either the square of the longest side, rather. We only call it the hypotenuse if we know it's a right triangle. The square of the longest side could be larger than the sum of the squares of the legs, or rather the other two shorter edges. And if that's the case, then you know that the triangle is obtuse, okay? Alternatively, a square of the longest side could be less than the sum of the squares of the two shorter sides, and in that case, the triangle is acute. So you'll have some homework exercises in which you dive into that a little bit. I don't have an example of that here. Just know that if the Pythagorean theorem test does not work out, you can still, by virtue of determining if your configuration of triangle lengths falls into either case 1 or case 2, determine that you have either an obtuse or acute triangle respectively. Okay, and we could talk about more examples of that in class. I'm going to just go ahead and move on to other examples for the purposes of this video, for what I have prepared. Okay, and now we're in the examples stage, in which I want to dive into several different examples that I took from the homework. They're not homework problems. Actually, they're like adjacent problems. They're probably even numbered problems that are very similar to stuff you'll be working on in homework. And here's the first example. The diagonals of a rhombus measure 6 meters and 8 meters. How long are each of the congruent sides? Now, if you recall from Chapter 5 Endeavors, Chapter 6, when we were in quadrilateral land, we talked about the diagonals of a rhombus being perpendicular bisectors of one another. That's a theorem that's going to really help us in determining the length of the congruent sides. And by sides, congruent sides, I mean the outer edges of the rhombus. We're going to figure that out together, remembering that for a rhombus, and here's a rhombus, I believe this is on your lecture notes as well, you want to add some notation to this, okay? First of all, you want to recognize that these diagonals that are in represented by the dashed lines here are perpendicular to one another, so you could put a right angle, or box in either of these 4 right triangles that are presented here by virtue of the incorporation of these 2 diagonals. I chose to put it here because I'm going to focus mainly on this right triangle AEB, okay? But take into account the entire lengths of these diagonals here that were given to us, right? 8 meters, I just went ahead and just left it as the numbers. It's going to be the longer diagonal, and the shorter diagonal will be the 6 meter long one. Now, not only are the diagonals perpendicular to each other, but they're also bisectors. So now I know that these edges right here that are formed by the diagonals intersecting one another, I'm talking about edges DE, EB are both of length 3. And then similarly but distinctly, AE and EC are both of length 4. How do I know that? Because I cut the 6 and 8 length diagonals exactly in half. Perpendicular bisector. Bisect means cut in half, right? Okay, so then we can clean up house a little bit and focus on triangle AEB, recognizing that we have the 2 legs lengths and it's a right triangle. So we could use the Pythagorean theorem right here in order to plug in those values and solve. Or you might recognize that you have 2 out of 3 of a Pythagorean triple and be able to conclude just by inspection that the hypotenuse of this little right triangle AEB, so I'm talking specifically about length AB, is going to be what? It's going to be 5. Spoiler alert, it's 5. Or you could always use the Pythagorean theorem to come to that conclusion thusly, okay? So AB is an outer edge of the rhombus, so each of the congruent sides, therefore, is 5 meters long. And you should attach the M for meters because there is a unit here for the lengths that are given to you. So the units should transfer along to your final answer as well. That's important. All right, so let me know if that requires some more discussion in class, okay? Moving on to the next example. Find the length of the altitude. Whew, so this problem is very involved and actually will more or less require, I would allow use of calculator for this particular problem, just as a heads up. And just know that the numbers that I would use for a similarly worded problem that you would see on the exam would be nicer numbers to work with, to where you would not even think about needing the use of a calculator. Okay, just so everyone's aware. All right, so what are we going to do here? So I'm just giving you a little bit of a heads up because I already know what's going to be involved in this problem. I don't want anyone to be too frightened here. But we are to find the length of an altitude to the 10-inch side of a triangle whose sides are 6, 8, and 10 inches in length. 6, 8, and 10, huh? That sounds like a familiar relationship in the lengths. Isn't that a scalar multiple of a 3, 4, 5? It is. If you take 3, 4, and 5 and you multiply all those edges by 2, you'll get 6, 8, and 10. Well, a 3, 4, 5 is a Pythagorean triple. So what kind of a triangle are we dealing with here? We're dealing with a right triangle. Now, it's not explicitly said that it's a right triangle in the prompt here. Like if you read it again carefully, you will notice that they do not categorize this triangle as a right triangle. So it's our job to recognize the value of the lengths that are given to us and to find the pattern. Okay, and this is somewhat challenging, and it's going to be something that you'll develop as you go in regard to putting in an appropriate amount of practice in these sections. So here we go, okay? Here is a right triangle ABC that I'm going to put an altitude to. So there's the altitude auxiliary line CD that I'm adding to it. And I'm going to go ahead and affix the appropriate lengths to what I know has to be a right triangle, because 6, 8, 10 is a scalar multiple of 3, 4, 5. Which is a Pythagorean triple. So it itself is a Pythagorean triple, and that's how I know that I'm dealing with a right triangle, even though it wasn't specified. So we want to find the length of this altitude. So we're going to use some of those geometric mean relationships that were presented to us earlier in this section in order to get at that. It's going to be a challenge, but I'm here to show you all of the details, okay? So let's first come up with the correct or a correct geometric mean proportion that's going to help us along the way. So I have chosen the one that relates the one of the edges, right? One of the legs to a segment of the hypotenuse and the entire hypotenuse here. So if I had it color-coded, right, BC would be the edge, the leg that I've chosen, the longer leg, and I'm going to say that that's the geometric mean of the entire hypotenuse AB, and the segment of that hypotenuse that's adjacent to that leg. That's the BD segment here, okay? Now that's going to allow me to find the length of the line segment BD. Now that's not the altitude that's being asked of us to find. There's not enough information at the moment with what was initially given to us to go straight to finding the length of this altitude. I wish it were so, but we're going to have to take an intermediate step to find either this hypotenuse segment, or you could have found the AD hypotenuse segment if you wanted to. I made a stylistic choice in saying I'm going to find the longer segment BD for no particular reason. Okay, and then once I have that longer segment BD, I'm going to Pythagorean theorem my way into finding the hypotenuse, not the hypotenuse. I'm going to, the altitude is what I meant to say. I'm going to Pythagorean theorem this longer leg of the original, the daddy or the largest triangle's leg, and then the segment here will be the longer leg of the medium right triangle, and then this 8-inch length becomes the hypotenuse of the medium-sized triangle, and so then I can Pythagorean theorem my way to getting the shorter leg of the medium right triangle. So hopefully everybody can follow along there. So here I have the proportion set up where the longer leg is the geometric mean of the hypotenuse of the main right triangle, the biggest one, and its hypotenuse segment that's adjacent to the leg I chose. Okay, plug in the values. 8, 8, 10. BD is unknown to us. That's what we're going to solve for. So take your cross product. You'll get 64 equals 10 BDs. I did not opt for the raised dot here to separate the 10 and the length of line segment BD. I hope that's okay for everybody. If you, in your particular notes that you're drawing up, the notes that you're adding to the lecture notes, if you choose to print them out, feel free to add a raised dot. Now, divide by 10 on both sides, and you'll get that BD is 6.4. Okay, yeah, it's a decimal. It's not, working out to be a very nice problem so far, but don't worry. I won't give you problems that involve too much in the way of decimals. Anything that's going to be hard to calculate by hand is not going to go on the exam, just so you know. But this is still good practice in using the relationship. It's being outlined here with the geometric mean of the altitude and the right triangle. Okay, so take your BD and couple it with the hypotenuse BC. Now, BC is the hypotenuse of the medium right triangle, okay? And put that into the Pythagorean theorem, right? BC is the hypotenuse of the medium right triangle. 6.4 is the leg, the longer leg that we just calculated. And CD is the shorter leg of the medium right triangle. So Pythagorean theorem will get us there. And now you may notice that algebraically we're going to have to take the square root at some point. Yeah. So taking the square root of a decimal number is no easy task and something that you are not expected to be able to do by hand. So in a test-taking situation, just hopefully no one is hyperventilating at this point. The idea of trying to take the square root of a decimal by hand, LOL, I would never let you have to do that on an exam. At this point, if you were tasked with something like this, at this point in your calculation, you would have a perfect square number equal to something squared. So you would be able to take the square root of it, by hand, like without doing any button pushing. But here you are expected to take the square root, and the square root of 23.04, if you do the button pushing, is really close to 4.8 inches. It's 4.80000 forever. It's like maybe like 15 or something zeros along the line. There might have been another digit, but not enough for my calculator to pick up. So for all intents and purposes, it's as close as we can get to 4.8 inches. Try it on your calculator and see what your calculator says. But when I do 23.04 and I take the square root of it, excuse me, insert square root. I'm just double checking it here. Delete. Okay, and then I press enter. Yeah, and I get 4.8, like straight up. Like really just 4.8. Okay, so the units are inches. So make sure that your final answer has inches, and we're done with this one. So like I said, pretty complicated with the use of decimals and having to take the square root of a decimal number. Please rest assured that you would not have to do that on an exam situation. I will give you nice numbers to work with, but you are still expected to understand and internalize this relationship here with the geometric mean of the altitude in relation to the hypotenuse and the line segment of that hypotenuse adjacent to the leg. Oh, sorry, that's not right. It was the relationship that was described here. Sorry, scratch what I just said. It's one of the legs of the main right triangle is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to that leg. Whew. Sorry, I misspoke earlier. Apologies for that. Okay, I believe we're ready to move on to the next example, and please let me know if we could talk about this one a little bit more in class, okay? All right, check this one out. We have quadrilateral ABCD with a diagonal AC added as this dashed line right here. And notice that there's a relationship between the dashed line diagonal and line segment DC. They happen to be perpendicular to each other, as mentioned here. Furthermore, AB and BC are perpendicular. So that's why we have these little boxes in these corners here to indicate that right angles are formed when perpendicular lines meet. If AB equals 4, BC equals 3, and DC equals 12, determine the length of DA, okay? Here we go. So let's go ahead and add the values that we know to be true. So here they are. These are the values that were given to us in the prompt here. And let's go through the motions of figuring out what the length of AD would be. Now the first thing that I would do is focus on right triangle ABC, okay? Because we have two of the legs' lengths figured out. And they look familiar, don't they? Notice that one length is of length 3, another length is of length 4, so the hypotenuse should be length 5, right? If you know your Pythagorean triples. Now, if you don't know your Pythagorean triples, you could always set up the Pythagorean theorem, and it would go like this. And you would eventually calculate that indeed the diagonal AC is of length 5. Now, notice that there's no units here, so don't worry about adding units to your final answer. Just the numbers are fine. So if AC is 5, we can go ahead and add that to our figure. I think that would be helpful. And now focus on right triangle ACD, okay? And ACD, now with the incorporation of this diagonal length, has two of its leg lengths known, and they are 5, 12. Oh, 5 and 12. That reminds me of another Pythagorean triple. There's a Pythagorean triple that's a 5, 12, 13. So you could go straight from there to determine the value of DA, which is the hypotenuse of the, larger right triangle in this quadrilateral, is of length 13. Or you could do the following calculations here with the Pythagorean theorem if you don't remember the 5, 12, 13 Pythagorean triple. Okay, Pythagorean triples are not necessary for you to memorize, but I really think they can help you get through your homework and your exams with, more quickly and with relative ease if you get to know your Pythagorean triples. So that's my advice, okay? I believe that this is the last example in 7.4 and that we are going to be, moving on to section 7.5 on special right triangles. Now, for 7.5, special right triangles, we have two different types of special right triangles. We have 45, 45, 90 special right triangle, which is an isosceles right triangle, okay? And we're going to learn the relationships between the side lengths that are going on here. And it's a very interesting relationship because you can be somewhat generic with it, okay? All you need to know is the length of one of the legs, because the other leg is the same length because it's an isosceles right triangle, right? So the two legs are equal in length, and then the hypotenuse is the square root of 2 multiplied by that leg length, okay? So here we go. Let me just add to this particular 45, 45, 90 generic right triangle that's given to us, triangle ABC I'm referring to in the figure, and let's add the relationship between the legs, which are unknown to us. It's true. We want to make this general, so it's like whatever the leg length for this right triangle is, we can calculate the other two lengths, okay? Because let's just say you knew the length of line segment AC. Let's say that X was equal to 2. Well, then line segment BC is also 2 because it's the same length. And then the hypotenuse of this particular right triangle, AB, would be root 2 times 2. So it would be 2 root 2's, okay? So that's just a very, specific example to this generic overview of the side length relationships for a 45, 45, 90 right triangle. It's a special right triangle, comes up a lot, so we want to learn this relationship. Okay, let's introduce the 30, 60, 90 right triangle. So here we go. Here's an example of a 30, 60, 90 right triangle. So the way that we want to get to know the relationship here is that it's easiest if you are given the length of the shortest leg. So we want to categorize that as being the most bare bones unknown possible. So we'll have that one be representing X. So if you know the length of your shorter leg, which is always opposite the 30-degree angle, there's a relationship there. It's already been alluded to a little bit with the inequalities of a triangle section that was in a previous chapter. The shorter leg is always opposite the 30-degree angle. The longer leg is root 3 times that shorter leg length of X, and the hypotenuse is always double the shortest leg, okay? So there's a relationship that's definitely in play here. If you ever have a right triangle whose leg length and hypotenuse have this, if you double the leg length, you get the hypotenuse length, then you know you have a 30, 60, 90. We'll talk about that a little bit later in a relevant example that's coming up. Okay, cool. So these are the lengths. And you know what? If you have any of the lengths here, it doesn't have to be the shortest leg. You can always calculate the rest of the edges here based on that. You just have to have one length and to know that you have a 30, 60, 90 right triangle. Okay? Cool. Now, the next two theorems are going to be the converse of the two theorems that have been presented so far. So here is basically the converse of the very first theorem, introducing the 45, 45, 90 right triangle, which is to say that if you have a right triangle, so actually there should be a box right here, right from the get-go. If it's a right triangle in which the two legs are of the same length, and therefore the hypotenuse is going to be root 2 times that leg length, then you know that you have a 45, 45, 90. So you can add those degree measurements in the following appropriate positions, okay? Cool. So this is the converse of the very first theorem, introducing the side length relationships for a 45, 45, 90. What this is saying is that if you have those particular side lengths of x, x, and root 2x, you can categorize your triangle as a 45, 45, 90. So it's just taking that same relationship but putting it together in the opposite order. Okay. Similarly, this fourth theorem is the converse of the second theorem. So what you have from the get-go is a right triangle in which one of the legs is exactly half of the hypotenuse, or said another way, the hypotenuse is double the length of that leg. If you know that to be the case and it's a right triangle to begin with, then we know that we have a 30, 60, 90 right triangle, a special right triangle 30, 60, 90, and we know that the 30-degree angle is always opposite of that unknown leg value that was half of the hypotenuse, okay? So the 30 degrees goes here, and you know this because that's the relationship that's being described in this theorem, okay? The 30-degree angle is always opposite the shorter leg, and so the 60 degrees goes in this position here, and the other, interior angle position. So that means the edge that's opposite the 60-degree angle must have a length of root 3 times 6. And that's kind of the order in which you could put the items together according to this theorem. Again, this is the theorem that's the converse of the introductory theorem for the 30, 60, 90 right triangle length relationship. Okay, moving on. Now let's use these relationships and be able to determine the lengths of certain edges in generic situations or specific ones, okay? And I went ahead and, for no particular reason, I think in a previous semester students were wondering which problems I was taking from the book to get the examples that I use for lecture. So I went ahead and put the numbers on them. So this is number 2 from your textbook in section 7.5. And so for the rest of the examples, it'll list which number it is, okay? And these are not ones that are assigned for homework, obviously. You're going to use fresh, odd-numbered problems for the homework, so you can look up the answers in the back of the book. And if any of the answers are omitted in the back of the book, they can be ones that would be good fodder for discussion in our class period, okay? So here we go. We are given that this is a 45, 45, 90 triangle right here. And we are given that AC, the length of line segment AC that is this unknown value of lowercase a. So go ahead and add that to your figure, like so, okay? And then we're going to use that information to find the length of line segment BC, which is the other leg. So if we have a 45, 45, 90 right triangle, what's going to be the value of the other leg? Well, it's going to be the same value as the leg that we were given. So it's going to be having a value of A. Oops, I'm getting ahead of myself here, okay? And so then, because it's a 45, 45, 90 right triangle, we know that the hypotenuse has to be root 2 times that leg length, which is root 2 times A. So that's it. This is meant to be a very straightforward, relatively easy example. Notice it's number 2 in the homework set, or the exercises in which the homework set comes from. So it's meant to be very straightforward. So if you're looking at this example and you're like, really, this is what we're doing today? Yeah, to start with, and they're going to get more challenging as we go. All right, let's move on to the next example. I'm going to do number 8 from the exercises in this section. Let's see, we're given right triangle XYZ, as seen here, and the measure of angle X is 45 degrees, and the length of line segment XY, which is the hypotenuse, is 12 root 2. So add this information to your triangle, and then draw some conclusions. Well, if we have a 45-degree angle here, and we know it's a right triangle, we know that this angle's measure has to be also 45 degrees. So we have a 45, 45, 90 right triangle. So go ahead and add that to your figure. And then say to yourself, all right, if I have the hypotenuse and it's 12 times root 2, well, then this 12 value, right, whatever's being multiplied by that root 2 factor, that's going to be the lengths of the, legs there, which is exactly what I'm being tasked with finding. XZ and YZ are the 2 leg lengths. They're both length 12, so you can go ahead and make this string equality statement as your final answer would be fine, or you could separate it into 2 separate statements distinctly saying that XZ equals 12 and YZ equals 12 if you like. But this is perfectly acceptable. Okay? Cool. Another relatively easy one. Let's move forward and get into something more challenging. Okay. Now, for number 12, we are given right triangle DEF with the measure of angle E is twice the measure of angle F. Okay, well, angle E and angle F are the 2, acute angles that have to, because they are the 2 angles that aren't the right angle within a right triangle. There was a theorem, if you recall, that says that these 2 angles need to be complementary. So if one angle is going to be twice the measure of the other angle and they have to sum to 90 degrees, there's only one possibility for the measures of angles E and F. And because they come out of this section, special right triangles, you could kind of use context clues to determine that the measure of angle E is going to be 60 and the measure of angle F is going to be 30, right? Because if you double the measure of angle F, it has to equal the measure of angle E, and they have to, sum to, 90 degrees. Furthermore, the length of line segment EF is 12 root 3. Interesting. Okay. And so EF is the hypotenuse, and we have a factor of root 3 in the hypotenuse, which is very strange. But it's nothing we can't handle. We just need to put our algebra hat on in order to find the lengths of our legs DE and DF. So here we go. Go ahead and add what you know to be true based on either the explicitly given information or the thing you can conclude based on this measure of angle E equals twice the measure of angle F. We were able to determine that must mean that F is a 30-degree angle and E is a 60-degree angle, okay? We could talk more about that in class if you like. Now, we have a 30, 60, 90 right triangle, and we know the hypotenuse is 12 root 3. So in order to find these legs, the first step that I'm going to do is to take the hypotenuse and cut it in half. Why would I do that? Because I know that's the relationship between the hypotenuse and the shorter leg, okay? So what is half of 12 root 3? but 6 root 3, right? You only cut the value outside of the radical in half because the stuff inside of the radical cannot be touched. It's like it's in jail. It's in radical jail, and it just comes along for the ride. It's its own, distinct factor that does not get manipulated outside of the radical, okay? So if we have 12 root 3's for our hypotenuse, half of that is 6 root 3's, and that's how I'm getting the shorter leg. The shorter leg is always opposite the 30-degree angle. Now, how do we use this 6 root 3 in order to find the value of DF, which is the longer leg? Well, we have to take the shorter leg value of 6 root 3 and multiply it by root 3. So what does that look like algebraically? Well, here it is. Here's 6 root 3 multiplied by a root 3. Those root 3's get multiplied together, and they become a 3, right? Because it's square root 3 times its other square root 3 counterpart becomes the square root of 9, technically, because you can have the multiplication occur inside of a single radical because of this algebraic rule that I'm sure everyone has some familiarity with, which is to say that the product of radicals is the radical of the product, right? The product, the multiplication goes inside of a single radical. And so that's how you get the square root of 9 here. Square root of 9 is 3. So hopefully everyone can follow that. And again, if you ever need more description on something algebraic that's being presented here in which you feel like there's not enough detail, I'm happy to go through it in class with more detail. You need only ask. 3 times 6 gives us the 18. So that's how we get 18 here as the length of DF. And I'm going to go ahead and present this in, bigger letters to explicitly answer these two lengths that we were asked to find. The length of D is 6 root 3, and the length of DF is 18, the lengths of our two legs. Okay, great. Moving on to the next example. Here's number 14. Let's say we were given a right triangle RST, which looks like it's kind of upside down, and furthermore, the hypotenuse seems to be extended with a line segment TV, okay? And that gives us an exterior angle STV, which they're giving us as 150 degrees, and furthermore RT, which is the length of the hypotenuse. So it's just the length from this edge, from this vertex to this vertex, not including the extension here. The hypotenuse is 6 root 2. Okay, so let's add those two pieces of information. And that's going to allow us to mark this interior angle at angle STR as what? Well, angle STR and angle STV are, supplementary to each other. They form together a straight angle. So they have to sum to 180 degrees. 150 degrees are used here for the measure of angle STV. So what, therefore, must be the measure of angle STR? It's got to be 30 degrees, right? Okay, good. Now, if this angle is 30 degrees inside of triangle RST, and it's a right triangle, then how many degrees are left? You guessed it. The measure of angle SRT is 60 degrees. We have a 30, 60, 90 right triangle, special right triangle. And we know the value of the hypotenuse. The hypotenuse has a length of 6 root 2. Using this, cut it in half, we'll be able to find the length of leg SR, the shorter leg. How do I know that SR is the shorter leg? Well, I could just look at the figure, but also it's the length that's opposite the 30-degree angle. So SR, therefore, or RS rather, as it's being named here in the find prompt, is going to be half of 6 root 2. So we have 6 root 2's here, half of that would be 3 root 2's. So go ahead and add that to your figure. Then we need to take this shorter length and multiply it by what to get the longer leg? You guessed it, root 3. So take your 3 root 2's, multiply it by root 3. Again, put your algebra hat on and recognize that the product of the radicals is the radical of the product. So that means that this root 3, root 2 multiplication here is going to turn into a single square root of 3 times 2, which is how you get your square root of 6. Now that can't be simplified any further, and I want you to give an exact answer anytime you're dealing with radicals. So that means that the value of ST here is going to be 3 root 6's. So go ahead and present that as your final answers for the lengths of the legs RS and ST. RS is 3 root 2's, ST is 3 root 6's. And there you have it. All right. Again, more is needed. Ask in class. Moving on to number 18. Ooh, create a drawing as needed. So this one's extra challenging because the things that are given here are not coinciding with a given figure. So the figure is something that we will need to draw, looking very carefully and critically at what was given to us. So we are given triangle XYZ with XY equals YZ equals XZ. You know what this means? All of the edges of this triangle are equal in length. So what kind of a triangle do we have here? What kind of a triangle has all of its edges equal in length? That would be an equilateral triangle. Furthermore, ZW, which is not one of the edges here, right? ZW is an auxiliary line that's perpendicular to XY. Okay, so we're going to have an auxiliary line, an altitude, in fact, that's going to meet the edge ZY, or XY rather, this edge right here, XY perpendicularly. So it's going to form a right angle with this point W is going to be on XY. Okay, that's what it's being said here explicitly with W on XY. And furthermore, YZ, which was an outer edge mentioned here, has a length of 6. Whew. Okay, so there's a lot of information here. I want you to actually follow along with me with the drawing, and I want you to, for the easiest application of all of this information, I want you to actually kind of robotically follow along with me and draw your equilateral triangle with the edges, the base vertices being X and Y, just like this, and your apex vertex being the Z. Okay? Then draw ZW, your altitude, like so. Okay? Feel free to add some boxes in the interior of the angles that are formed with this altitude being incorporated. And don't forget to label this point right here as W. Now, YZ, which is right here, this edge right here, has a length of 6. But remember, it's an equilateral triangle, so all of the edges are of length 6. You can go ahead and add 6s all the way around. So, because it's an equilateral triangle, it's also equiangular. So that allows me to have all of the interior angles be 60 degrees in measure. And since this altitude also acts as an angle bisector, but also we have a 90 here and a 60 there. So in regard to either one of these interior right triangles, let's maybe focus on ZWY. We know that this angle right here is a 30-degree angle. You guys feel me on this? Angle WZY is 30 degrees because that's the number of degrees that are left for the right triangle ZWY. Okay? Now we're trying to find the length of ZW. Notice that the triangle ZWY is a 30, 60, 90 right triangle. We know the hypotenuse, right? So the hypotenuse can be cut in half to find the smaller leg WY of 3. Okay, and then take that smaller leg, multiply it by root 3, and that'll give you the altitude ZW, which is also the longer leg of the 30, 60, 90 right triangle inside of the equilateral triangle. And that gives you your final answer, ZW, having a length of 3 root 3. All right, cool. Moving on. I think we have maybe 2 or 3 more examples. Yeah, you have a wealth of examples in this section. Hopefully that garners some ability for y'all to get through most of this homework unscathed. But mind you, the class period is definitely a good time to go over any of these things that are not hitting right the first time. Okay, cool. Again, we need to create a drawing as needed for number 22, and this time we're dealing with a rhombus, ABCD, in which diagonals AC and DB intersect at point E, and that DB, AB both equal 8. Whew, a lot of information here. Let's start drawing in order to eventually find the length of AC. Okay, which is the length of the other diagonal. We're given the one diagonal length of DB, which is an 8. Okay, so here is a triangle, and I highly recommend that you follow along with my drawing the way that it's presented. A, B, C, D in this order. I highly recommend and make your rhombus relatively this shape. Now, a rhombus has to have congruent exterior edges all the way around, so make sure that that is definitely in play. Okay, go ahead and add diagonals AC and DB, And I recommend that you have them, oh, well, you have to, because the given information is to say that they intersect at point E. And feel free to add a little box inside of the interior of one of the right triangles. I usually, when I have to draw diagonals in a rhombus, I usually put the square that indicates the right angle in the same position every time. But inside the interior of any of these 4 right triangles that are formed with the intersection of the diagonals is perfectly fine. Okay, AB is length 8, and so is DB. So go ahead and add that to your figure. But recognize that rhombi, a rhombus's diagonals are perpendicular bisectors of one another. So what has to be the length of EB? Well, it's got to be of length 4, right? Because it's bisecting that diagonal of DB of length 8. Cool. Look at this, guys. We have a right triangle in which one of the legs is half the length of the hypotenuse. What kind of a right triangle are we dealing with? We're dealing with a 30, 60, 90. We know it because of the relationship between that leg and the hypotenuse as being like half or double depending on which direction you're looking at the relationship. So that means we have the 30-degree angle here, the 60-degree angle there, and what has to be the length of AE? Like, we want to find the length of AE so we can eventually find the length of AC, recognizing that AC is going to be double AE because of the bisecting nature of these diagonals. But that's getting ahead of ourselves. What is the length from A to E? Well, it's going to be the shorter leg of 4 multiplied by root 3. So that'll be 4 root 3, but then double it to get the length of the full diagonal, and that's how we get AC having a length of 8 root 3s. Okay? Cool. So fun. 30, 60, 90 right triangles. I just love this stuff. Okay, so that was a bit fast, but feel free to rewatch this, right, if there were details that you felt like slipped through the cracks the first time around. And also, I'm happy to demonstrate this a little bit slower and with more detail in class. Like I've said so many times before, you're tired of hearing it, you need only ask. Next example, ooh, yeah, we've got a little bit of a word problem here with some boats that are being launched off of a centralized location here, and we're using a little bit of a compass configuration, north, south, east, west. So north, south, east, west intersecting lines like this are assumed to be perpendicular. That's an assumption that we need to make here, and also the straight line distance that you see dashed here that we're eventually going to calculate, that's going to be perpendicular to this eastwardly directed line. Okay, so that's just an assumption that I want to present right away in the midst of this example, so we know that we're dealing with some right triangles here, special ones at that. Okay, let's read the example. It says Mara's boat leaves the dock at the same time as Meg's boat. Okay, and the dock is right here, this intersection between the north-south, east-west poles, okay? And Mara's boat travels due east at 12 miles per hour, okay? So here's Mara's boat location where it launches, and it's traveling here. And this is the end location after a half hour. That information hasn't been presented to us yet, but here we go. Here's Mara traveling, and she's going due east, okay? Meg's boat travels 24 miles per hour, so twice as fast as Mara's boat. Just keep that in mind. And in the direction of north 30 degrees east. So it's a 30 degrees, right, deviation from north in the easterly direction. Hopefully that makes some sense here, even if we're not, navigators, in this class. Hopefully that makes some sense. We deviated 30 degrees from due north in the easterly direction, and that's how we're configuring Meg's directionality for her boat. To the nearest tenth of a mile, how far apart will the boats be in a half an hour? So we need to recognize that this is a distance, rate, time situation. So there's a relationship between the distance, the rate, and the time of a moving body, and it's this. The distance is equal to the rate times the time. And there it is. Distance equals rate times time. If you know this relationship, you can get through a lot of word problems of this type, okay? So we need to keep this in mind in order to calculate how far apart the boats will be in a half hour. Okay, so we need to figure out the lengths of these arrows right here, which determine the distance that Meg and Mara have traveled after this half-hour time that's all been allotted to them. Okay, so from the origin, that's the launching off point right here, Meg's distance is as follows. We have her rate as 24 miles in 1 hour, okay, times 0.5 or a half an hour, right? So when you are dealing with rates times the time values should cancel out and you'll just be left with the distance, which is why the distance is equal to the rate times time works out as far as the units are concerned, okay? So just think of these hours as being kind of slashed away here, and you'll just be left with how many miles? Well, what's 24 times 0.5? That'll be 12 miles. So that means that Meg has traveled 12 miles. So I'm labeling it here like this, okay? Great. Let's calculate Mara's distance. Well, she had a rate of 12 miles per hour, 12 miles over 1 hour, and that's going to be multiplied by that same duration of half an hour. The hours again will cancel, and we'll be left with 12 miles times 0.5, which is going to be 6 miles. Check this out. So look, we have what has to be a right triangle because we have to make this assumption of a right angle right here, okay? And we have one leg is half the distance of the hypotenuse. So we know we have a 30, 60, 90 situation here. And that's going to allow us to configure this dashed line distance, which is the straight line distance between Meg's location and Mara's location, as 6, the shorter leg's distance times root 3 miles, which if we're trying to determine to the nearest tenth of a mile, we would have to punch this into a calculator and round to the nearest tenth of a value, which would be 10.4, and then don't forget to affix the appropriate units. Now, would a problem just like this with the same numbers be on your exam? Well, no, because the numbers aren't, very fun to work with, and the final answer of having to determine the tenth of a mile approximation by hand would be something I would never ask you to do. So if you had this problem or something like that on the exam, I would ask you to give an exact answer in which you would keep it as the 6 root 3 miles. Okay, you would stop here. So up until this point where we get the decimal approximation, everything that happened previous to that in regard to this the workup of this problem is totally fair game for an exam problem, just so you guys know. All right, I believe we have one more example to tackle, and then we are done with this extremely long and example riddled lecture video. And here it is. Let's consider triangle STV, and it's an isosceles right triangle. So that tells you right away that ST and VT have the same length because it's an isosceles, and the hypotenuse is given as a length of 20. M and N are midpoints of ST and SV. Ooh, so remember that theorem that said if you connected the two midpoints on the edges of a triangle, then you would create a line segment inside that triangle that's not only parallel to the third side, but also half its length. That's going to be wildly important to the workup of this particular problem. And so we'll want to recall that. Again, the theorem is paraphrased as the following. If you have a triangle in which two of the edge's midpoints are connected, then the line segment formed is parallel to the third line, and it's half the length of the third line. So that means that we could state right away that MN is half the length of VT or TV, however you want to name that last line segment. Okay, so eventually we need to find the length of MN. So that's going to be very important for us to understand that relationship. So let's move forward with some things that we know to be true. Now, if we have an isosceles right triangle, we have a 45, 45, 90. Oh, furthermore, okay, so what did I say? Look at this. So I put in that since N is a midpoint, I know that this length is 10 and this other length is 10, right? Because N was categorized as a midpoint of SV, right? Yes. Furthermore, because these two lines are parallel, right, the connection of the midpoints makes a line segment that's parallel to the third line, and this angle right here was a right angle, I know that this angle SMN also has to be a right angle, because when parallel lines are cut by a transversal, in this case, the parallel lines are MN and TV, and they're cut by a transversal ST, then corresponding angles are congruent, right? So if this angle has to be 90 degrees, then this other congruent angle also has to be 90 degrees. So I have this interior right triangle that's also, I could categorize it as isosceles because this is a midpoint. So that's also going to be, having the same length here as half of that. So here we go. Let's go ahead and let those be unknown to us. And let's, either we could Pythagorean theorem this thing, or we should be using the special right triangles business, because we know that this is another 45, 45, 90, right? So we're going to have 10 be equal to the square root of 2 times that unknown length, right? Okay, so we divide both sides by root 2, but then rationalize the denominator, and we're going to eventually come up with x as being a length of 5 root 2. But remember, x was just a placeholder algebraically for the length of mn, so that's how we're getting mn as our final answer being of length 5 root 2. Whew, okay. That was a fun one. So there's some details here that aren't explicitly on the figure that you could add, and that's categorizing this interior triangle, SMN, and also the exterior triangle of STV as being a 45-45 right, 90 right triangle. And I mean, that's a direct consequence of this isosceles categorization being put in the given information for triangle STV, and then we found that this interior triangle was similar to it, so therefore also had to be a 45, 45, 90. Cool. Again, more detail needed? Ask in class. I will see you soon for that very purpose, and these are the homework sets that I recommend that you try before I see you in class associated with this lecture video. So that'll be, again, week, what was it? I said it at the beginning of the video. I'm not going to repeat it again because I don't really remember. But I will see you soon when we talk about 7.4 and 7.5 in class. Looking forward to it. Until then, you have a great day.